Okay, so in the last video we looked at how hydride ions can react with carbonyl compounds in a nucleophilic addition reaction. Here we're going to have a look at what happens when one of the products, when the product formed has an asymmetric carbon atom. Now in the other two examples, the products didn't have them, but so let's think about butanone then. Okay, if we react, so we've got butanone. I'll move it down a little bit. Okay, so butanone, we don't have to call it butan 2-one because, of course, if it was, it can only go, if it was on this carbon, it would still be butan 2-one. If it was on this carbon, then it would be butanal. So butanone, we don't need to put any numbers there. Right, here's the hydride ion. Okay. Right, that's going to attack this carbon, which is delta positive. So that pair of electrons goes onto there, and then the pi bond breaks in the carbonyl, both electrons going onto the oxygen. So we are going to form this intermediate. And we've got the new hydrogen there, and the ethyl group here. And of course, the final step is for that to pick up a proton from the solvent. So draw a pair of electrons from here, going onto that. Okay, so we end up with butan 2-ol as the product. And it probably hasn't escaped your notice that this carbon is asymmetric. You've got 4 different groups attached to it. You've got a methyl group, a hydrogen, a hydroxide group, and an ethyl group. So 4 different groups, so it can show it can exist as 2 optical isomers. Now, if you actually look at which optical isomer is formed, you actually get a 50-50 mixture of both. Of both isomers. So that means that mixture will not be optically active. And what do we mean by optically active? Well, it means it won't rotate the plane of polarization of polarized light, because one lot of the isomers will rotate it one way and the other lot will all rotate it back the other way. So it looks like it's not doing anything, so it's not optically active. And this has got a special name. It is called a racemic mixture. So the question is, why do we get a racemic mixture? And we need to think about the stereochemistry here. So if we think about, let's think about the carbonyl carbon here, put an asterisk on it. There are 3 different groups around that, and there's no lone pairs. When we have a double bond, you just treat it as a single, don't you? So 3 groups, 3 bonding pairs, no lone pairs. What's the shape of that going to be? It's going to be trigonal planar. So let's see what happens there. Okay, so I'm going to try and draw that, show a little bit of the shape of it. So I'll draw this as a flat structure, because that's all on one piece of paper. So you've got 1 carbon there. Here's your central carbon. We've got the methyl group here. We've got the carbonyl group there, and we've got the ethyl group here, C2H5. Okay, and that is this flat around here. All of these bond angles are all 120 degrees. Okay, so this is we've got a planar carbon atom. Right, now that's going to be attacked by the nucleophile, which is H minus. Now the H minus is not going to attack around here or here because there's loads of electrons on the oxygen, the C2H5, or here. Okay, so where it was going to approach from above or below where there's fewer electrons. So it can, let's draw a blue hydride ion there. So the blue one is going to attack from below. Right, so it's either, that's the easiest way in, and it's going to be equally likely that the red one or the blue one happens. So if the blue one comes in, that's going to go like that, and you're going to see that will, this carbon has now got not 3 groups attached, but it's got 4 groups attached. So the shape is going to be tetrahedral. Okay, so there's our new hydrogen attached there. There's our methyl. There's the C2H5 going back into the plane of the paper. This blue hydrogen's coming forward, and then we've got the oxygen, which is going to pick up a proton and become OH. Okay, so we're going to get that happening there. Let's think, on the other hand, if the red one attacks, so the red one is going to attack from above, and you get the opposite optical isomer there. You get the mirror image formed. So if you, with that one, you're going to get carbon. Here's our new hydrogen attached there, but in this case, it's going to be C2H5 on that side there. It's going to be the methyl group there, and your OH there. So these two are mirror images, non-superimposable mirror images. So they are, and each one's equally like to form. So you get a 50-50 mixture. You get, it's called a racemic mixture. This is typically, you get like a 3-mark question, and it would say why why isn't the product, explain why the product isn't optically active, and you say, well, because you get a racemic mixture. And why do you get a racemic mixture? Well, because the ketone is planar, and the hydride ion can either attack from above or below, and each one is equally likely to happen. Okay, so that is what happens if you've got the product with an asymmetric carbon atom in it.